Now that we've covered how climate change works and the pace of warming that we have currently put ourselves on, let's talk about what that means for human civilization. The What's at Risk section covers the weather impacts of climate change, the feedback loops that could make warming spiral in on itself and accelerate faster and faster in a vicious cycle, the air pollution damage that fossil fuels pose to human health and lives, the cost trade-offs that we face because there are no easy choices here. The key case here is that fossil fuel use and climate change are not a future threat. They unleash severe pollution and climate damage today that is only getting worse, and they make Earth a more hostile home for human life. Let's start by diving into what I call the Climate Change Weather Report. Now, this is a broad overview of the top impacts that climate change has on extreme weather and ecosystem damage. This is an incredibly broad and complicated field that could merit a full deck on its own. So here, just highlighting the top effects. And as a way to organize them, I like to break them into fire and water, and into extreme weather and steady damage. So on the fire extreme weather side, the warmer atmosphere causes fiercer, more frequent heat waves and longer, more severe droughts. On the water side, warmer air can actually hold more water vapor. So it can take longer for rain to build up, and then when it does rain, it can rain harder, which can cause severe flooding. Ocean heat is also the fuel for hurricanes. So the warmer the oceans get, the bigger and stronger hurricanes become. On the steady damage side for fire, there are many impacts here, but the most important ones are insects, including ones that bear diseases and eat crops, thriving and expanding their territory. Also, crops are affected by more erratic growing seasons. Higher carbon dioxide, also for reasons that are still being researched, causes nutrition levels in staple crops to decrease. These are both critical impacts to food supplies, especially in developing countries. And then on the water side, we don't only have the sea level rising, we also have, as oceans absorb more and more heat and more carbon dioxide, they become hotter and more acidic. And this is having severe consequences for marine life. Globally, coral reefs are dying at an alarming rate. And it also has effects on the entire ocean ecosystems on which many people depend. In terms of impacts, I originally tried to make a version of the chart that would clearly link each cause to each impact, and I had to give up. It was too complicated. But altogether, these trends drive many ways to threaten human life. The fire ones result in fiercer wildfire seasons. Several effects here contribute to higher rates of infectious disease. Many disrupt agriculture, both livestock and crops, drive collapse of ocean ecosystems and the destruction of food supplies that many communities depend on, the destruction of freshwater sources, increased flooding, which is sometimes temporary, and sometimes as the ocean rises, the effect of coastal submergence becomes permanent and threatens coastal communities around the world. One area we should especially talk more about is the way that climate change affects extreme weather. This slide shows what I call the Extreme Weather Speedometer, which is a visualization tool for how climate change impacts any one given region's weather patterns. So let's take California as an example and look at this box on the left. In any given year, weather swings from year to year. So it can land in that normal range in which it's going to be a relatively regular year, or it can fall into those extreme ranges, and you can have an especially bad year of wildfires or some kind of flooding. In California, because the state has a natural wildfire season, the fire risk is already higher than the water risk. Now, in an area that has fewer fires, but it's more prone to hurricanes, that might be reversed, with that blue zone being larger and the red zone being smaller. Now, what climate change does is it expands those extreme zones. So in any given year, it's now more likely that that needle is going to fall into either the extreme fire or the extreme water zone. It doesn't mean that every year is going to be extreme. It's still possible for that needle to fall into the normal range. it just becomes less and less likely. Another impact is that it raises the severity of any given extreme weather season. So if you look at the worst possible fire season in the pre-industrial age and compare it to the worst possible fire season today in California, the one today can be a lot worse. And the actual number values on this chart, just to confirm, are hypothetical. This is a tool for visualization to wrap our heads around a very complex issue. But let's look on the next slide at how this actually looks if we overlay California's last decade of weather onto this framework. To look at California's last decade, we need to start with the brutal drought of 2011 to 2017, which set the stage for everything that would come later. Things flipped completely the other way in 2016 to 2017 when a massive burst of severe rainfall caused serious flooding, almost breaking through California's second largest reservoir, which would have unleashed a huge amount of damage. Almost 200,000 people had to be evacuated. This goes to show that climate change does not only exacerbate things in the direction of fire-related events, it pushes things up in both directions. And swinging back and forth between those two extremes can be even more destabilizing than getting stuck with one. Things swung back the other way in 2018 with California's most destructive fire season in recorded history. 2 million acres were burned and a huge amount of damage done. 2019 was actually a moderate year, again driving home the point that climate change does not mean that every year is going to be extreme. It just means that normal years become less and less likely. And finally, the decade was rounded out with 2020, when California had over 4 million acres burned, shattering the record set in 2018 for largest fire season in modern history. Now, the damage at the time of this writing from 2020's fire season was still being tallied. But in 2018, that amount of burning caused cost estimates ranging from $24 to $350 billion. So this really drives home the point of how much damage this can do, even in the world's wealthiest country, which in theory should be prepared to absorb these costs. Let's take a minute here to look at a question that causes a lot of confusion. As I said on the last slide there, California has had natural wildfire seasons, even before the industrial era. There has been extreme weather happening naturally throughout human history, throughout the world. So how can we be sure that recent extreme events actually are accelerated by climate change? How do we know that we just have not had a really unlucky couple of decades? And there are a couple of ways that we can prove that climate change is playing a major role here. But to be fair, climate modeling is not yet perfect. Weather and climate are incredibly complex processes, and even the most advanced supercomputers that we have today are not capable of perfectly modeling them. So yeah, this is why if you're trying to check, a couple of weekends out whether the weather is going to be clear, you can't be sure whether that forecast is actually going to be correct. Systems are getting better and better, but they're not perfect yet. Now that said, as the science gets better and better, and as climate change gets worse and worse, scientists are now able to point increasingly often to specific events that climate change has played a major role in. Things like this 2018 heat wave in Japan, which was assessed as impossible without human-caused climate change, to evidence that Australia's catastrophic 2019 wildfire season, its conditions were much more likely because of human-caused climate change. Brutal 2020 heat wave and wildfire season in Russia, which by itself emitted more carbon dioxide than Switzerland or Norway does annually, just through trees being burned. That was assessed as nearly impossible without human-caused climate change. And now, to be fair, there are other trends accelerating the damage as well. For instance, in California for wildfire seasons, there are some misguided fire management policies, which have helped make those blazes worse. Some damage is also caused by more human towns moving deeper and deeper into what used to be wilderness, meaning that there is more property to destroy. But we can prove that climate change is one of, if not the leading driver of this escalating damage as well. Scientific evidence can confirm, even when we're not able to say in specific event, X percent of damage would have happened naturally and Y percent happened because of climate change. Even when we can't say that, we can prove that the natural conditions that cause extreme weather, such as heat in the atmosphere and oceans, are worsened by climate change. With that in mind, let's back out and look at some other global examples of extreme weather events and the damage that they do. One is in the Southeast United States in 2017, when back-to-back hurricanes broke into the top 5 list of costliest hurricanes, 3 separate consecutive ones getting into that top 5 in a single year, causing devastating damage to Puerto Rico especially. In Syria, when a drought from 2006 to 2011, the worst drought the country had suffered in recorded history, destroyed the country's agricultural economy, both upending its employment market and destroying its food supply, helping to spark the 2011 eruption of civil war, which is still ongoing. It has a massive death toll, displaced half of the pre-war population, and caused global repercussions and aftershocks. Looking at Yemen in 2015, when 2 cyclones, one of them the first hurricane-strength storm to hit Yemen in recorded history, hit within 10 days of each other. These drove a locust infestation that also destroyed the agricultural economy, deepening a famine and worsening an ongoing civil war that the UN has declared the worst humanitarian crisis on Earth, continuing today. And then again, going back to Australia, when from 2017 to 2019, a terrible drought led to the driest spring and the hottest year in Australia's history, kicking off a terrible wildfire season. The fires burned a land area the size of England. They sent up clouds of smoke that circled around the entire planet and returned to their point of origin. This just goes to show that extreme weather can make the world's wealthiest nations look like developing countries with helicopter evacuations of citizens from beaches. And when things are that bad, even in the wealthiest countries on Earth, then in countries that are already on the precipice of chaos, extreme weather events can throw them fully off the edge, causing massively destabilizing events, sending millions of people from their homes. And these crises do not stay within those countries. They affect the entire planet. This is a fight that we are all in together. Now, extreme weather is not the only critical long-term threat that we need to worry about. Let's talk about feedback loops. So these are natural processes that rising temperatures accelerate, which themselves lead to further heating, creating a vicious cycle that makes climate change worse and worse. The first we're going to talk about is thawing permafrost. Permafrost is a layer of year-round frozen soil. It spans 6 billion acres across northern Canada, Russia, and other northern countries. And in previous eras of Earth's history, when the climate was warmer, that land used to be covered by ancient grasslands and forests. And once the climate changed and it became too cold, that life fell to the ground and was buried under this frozen soil. So the frozen soil locks away 1,600 gigatons of carbon, which is about twice as much as is in the entire atmosphere today. That's a gigantic carbon sink, and it's critically important that that stays locked up. However, as rising temperatures melt the permafrost, then huge amounts of carbon dioxide and methane from that buried organic life are being released into the atmosphere. So looking at this trend, again, faster thawing from higher global temperatures drives the thawing of permafrost. and that increases greenhouse gas emissions, increasing the amount of greenhouse gases in the atmosphere, leading again to even higher global temperatures in a chain that repeats itself. And for an image of what this looks like, this is a crater in Russia, where as permafrost melted and the ice in the ground contracted, the land collapsed in on itself. That crater is almost 300 feet deep. It is advancing at 30 feet per year, and it's over 3,000 feet long. I definitely recommend looking at the links here and seeing the images from drones that have gone into that crater and looked at the size and seeing those layers of soil. It's really fascinating and just absolutely otherworldly. And now, actually, I said it is about 300 feet deep. Those values were as of February 2018, so it has been growing since then. What impact does this have overall? Permafrost emits about 0.3 to 0.6 gigatons of carbon per year. That's about as much as Australia emits in any year. In addition, it emits methane, an even stronger greenhouse gas. And once again, the threat here is that the more Earth warms, the faster this accelerates, and the more this contributes to even more warming. As if that wasn't enough, let's talk about a second feedback loop, the melting of sea ice. So as the Earth has warmed, summer ice in the Arctic has shrunk about 13% per decade since 1979. It might be entirely gone as early as 2035 on current projections. Now, why does this matter for heating? Because of something called the albedo effect. And this is what's happening when, if you've ever noticed on a summer day, how much more heat is absorbed by black surfaces like asphalt as opposed to surfaces that have been painted white. Now, that's because a surface that is bright is reflecting a lot of light. Ice that is covered with snow reflects around 90% of the solar energy that hits it and only absorbs 10% as heat. However, dark seawater, like asphalt on summer day, absorbs far more heat. It only reflects around 6% of light and absorbs 94% of that energy. So as a result, when a piece of ice and a patch of seawater are both being hit by sunlight, the water is heating up a lot more than that ice. So the more ice melts into the ocean and becomes seawater, the more heat the water absorbs faster and faster, melting even more ice and accelerating the trend. So to summarize, higher global temperatures mean that sea ice melts faster, and that in turn means that the Arctic especially, and the globe overall, absorb more and more heat from the sun. Now, how big an effect does this have overall? Recent research suggests that the increased warming effect from melting ice has added about a quarter as much heating as the rise in atmospheric carbon dioxide. This is a massive acceleration of climate change that itself is driving further melting. This doesn't just have a critical and catastrophic impact on the ecosystems that exist on the North Pole. This is threatening the entire planet with faster and faster climate change. One critical detail to talk about here is that feedback loops are a top priority area for further scientific research. There are a lot of scientists digging into the melting of permafrost and sea ice and how they affect climate change. So this is an area where new findings are coming out all the time. Scientists do reflect these findings in their forecasts of warming, but say you had a report that came out as recently as 2018 and some new finding comes out in 2020, that relatively recent report will not have reflected the latest updates yet. So this is an area where scientists are continuing to refine our assumptions. So definitely an area to watch for further updates, but also an area to really try to keep track of the different opinions, because there's an active scientific debate over these. There's no question that these are critically important trends that are accelerating global warming, but there is debate over exactly how they're going to affect that trend, especially as we hopefully can get our emissions under control. So this is especially an area where I recommend diving into the sources that are contained here and using that as a launch point to go and look at what the latest updates have been from the scientific community. This deck so far has focused on the effects of climate change, but let's actually back out from that for a minute to talk about the air pollution damage that is caused by fossil fuels. Now, this air pollution is estimated to cause $2.9 trillion in global economic damage per year. That's equivalent to 3.3% of the total output of global goods and services. Now, what form does this come in? First, in premature death. Air pollution is the world's fourth leading risk factor for death. And then in lost work hours as well, even in non-lethal cases when people are made sick by air pollution or related diseases and cannot go to work. And from severe healthcare costs, not just for chronic sicknesses in adults, but this is especially severe for children who are born with conditions that will affect the rest of their lives. Now, these are all cases where staggering scale of human tragedy intersects with a massive amount of economic damage. Now, if we look at the national level, China and India are two of the countries that suffer the most from this, but even in the US, where the air is significantly cleaner, suffers $600 billion of damage per year, almost 250,000 premature deaths due to fossil fuel air pollution. If we zoom in on what the US could gain from moving beyond fossil fuels, a recent study has shown that if the world adopted enough clean energy to limit global warming to 2 degrees Celsius, that would come with follow-on benefits of $37 trillion over 50 years just for the US alone. That's $700 billion a year in savings from avoided pollution and climate impact costs. It was mostly made up of pollution. And so this goes to show that even if we take climate change out of the equation, there is still a huge rationale for moving beyond fossil fuels, both in terms of avoided human tragedy and avoided economic costs. Now, with that cost trade-off in mind, let's talk about what I call the cost menu that we're choosing from. Moving beyond fossil fuels is going to require huge investment. This on the left in blue references a study that estimates that $95 trillion are going to be invested in energy between 2020 and 2050. And saying that if we take the part of that investment that is planned to go to fossil fuels and shift it towards clean technology, and then add another $15 trillion in clean technology investments on top of that, we are actually going to be able to limit warming to 2 degrees with that amount of spending. And $15 trillion over 30 years, $500 billion per year, that is a lot of money to invest. But every $1 invested is going to have a 3 times to 7 times payoff in reduced pollution costs and reduced fossil fuel subsidies. And if we compare that number to the kind of costs that we're already paying for our dependence on fossil fuels, it starts to look more manageable. So here, and the circle sizes are proportional to the size of the spending. Here is that $2.9 trillion of annual costs that we just talked about on the last slide, imposed on the world through air pollution. In addition to that, here is a recent estimate looking at the amount of damage we are going to suffer from climate change itself, and it looks at about $863 billion per year, even if we only warm by 2 degrees Celsius. That means that if we warm by more, those costs are going to expand very quickly. So no one is saying that developing a global renewable economy is going to be cheap or easy. It's going to take a lot of upfront investment and relentless, disciplined progress over decades. But the faster we do it, the more money we are going to save in the long run by reducing the crippling human and economic damage that are imposed when fossil fuels drive air pollution and climate change. And for all of those who have made it through both of these sections, thank you for sticking it out, because we're about to finally get to the part where things get a bit more optimistic, to look at the technologies that we are going to be able to use to solve this challenge. So let's jump into that next.